I did a closed pipe resonator, and the name's kind of giving it away, like closed pipe. And so it's basically like a tube of some sort, but one end is closed and one is open, like a pill bottle. So that's like what a closed pipe is. And you guys should know how in pipes like this, what's actually moving is the air. So like I guess that's the air that's moving. That's in here. And in a closed pipe, the air vibrates on the sides and then hits the bottom and then it comes back out. And that's how it works. And then since this is the opening, it has more room to move. And since this is the bottom, there's less room for it to move, and therefore that means like when it makes its standing waves, this part is going to be the node and this is going to be the antinode. So here's the diagram I made, just in case you didn't get it. Antinode, node. So that's when it's most displaced and the wave can move, and the node is where it is not displaced at all. And then, so when it makes its standing waves, there's this thing, and it's called the fundamental frequency, right there. And that's basically when it's a wave that's like this, and you know wave is from like, would be from here, and then it would go like that. That's one wave. And then so therefore, this is 1/4 of a wave. This part. So you know the wavelength at the fundamental frequency, the wavelength is 1/4. At the fundamental frequency, the length is 1/4 of the wavelength, like the whole wave. Yep. And there's also this thing with like harmonics and stuff, and that has to do with different like standing waves and stuff. And so when you make the wave, like I'll say this one with a higher frequency, because it's a closed resonator, like it's closed at one end, it's gonna be like no even harmonics. Like the only harmonics are gonna be the odd ones, like 1, and then this could be like 3. And then there's also something with overtone, and it's maybe like 1, 2. That's like the end parts of a wavelength. And here's a formula for finding out the wavelength for closed pipe resonators. Yeah. And then the other thing has to do with resonators itself. So in case you don't know what a resonator is, it's kind of how, like an example they use a lot is with the tuning forks, like the ones we use in class, where you hit on your shoe and then it vibrates. So what they do is they take our hollow tube, this, and you put it in water, and that makes it like a closed end. And then of course, like usual, if you change this, it's gonna change the sound because it's the different like amounts of the pipe. You know, this is gonna change where the end is on the pipe, so it'll be different lengths. Anyway, but then the resonator would be when something like a tuning fork, and the tuning fork has a certain frequency. And so when you hit the tuning fork and it's vibrating, you put it on over top of this, and then the waves get sent down at that frequency in here. So it's like moving something else at that same frequency. And that's basically what a resonator is. Like where you have something moving, like the tuning fork, imaginary tuning fork, and then it moves the waves and it's the same frequency. And a lot of times with this, they mention natural frequency, and that's just kind of like the frequency if a system like naturally vibrated, that's what it would go to, like the standing wave would be. Yeah. And there's kind of this thing with harmonics, and I basically already talked about that. Never mind. Closed pipe resonator. Yay.